Welcome, the learner. You're here because you want to get right to the core of complex subjects, figure out what makes them work, without wading through tons of extra detail.
Exactly. And today we're tackling avionics.
Right, the communication and navigation systems in aircraft. Absolutely crucial stuff.
We've got this comprehensive source, Chapter 11 Communication and Navigation.pdf. It covers, well, pretty much everything. The history, the fundamentals, all the different systems.
So our mission today is, basically, to pull out the really key insights from this chapter, give you a solid understanding of how planes talk to each other and find their way.
From the very beginning right up to the super sophisticated tech we see now.
And keep it clear, keep it engaging.
It's quite a journey, you know? From just basic, often crackly voice radio, which was revolutionary back then.
Oh, I bet.
To the incredibly precise GPS navigation we all take for granted now. It really shows how electronics and aviation just, well, grew up together.
Okay, let's jump in then. The dawn of avionics. What really kicked things off? What were the initial drivers?
Well, the chapter highlights safety and just making flying more practical, more functional. Once planes could reliably stay in the air, the next big step was making them safer and usable in, different conditions.
Makes sense. And those early developments?
Yeah.
It sounds like things moved pretty fast.
He really did. First, big hurdle. Clear voice communication over radio. Ground to air, that was huge.
Game changer.
Totally. Then came navigational radios. Interestingly, the term avionics itself didn't really catch on until the 1970s, apparently.
Huh, really? So they had electrical stuff before then, obviously.
Oh, yeah, for sure. But proper solid-state electronics, the widespread use, that really hit its stride in the 1960s.
And World War I, that must have pushed things along.
Massively. The chapter points to the urgent need in wartime. Ground to air to air, voice comms, they became absolutely critical for coordinating flights. That tech got developed because it was needed right then.
Then into the 1920s, civilian flying starts booming. What were the priorities then?
Right, so with more civilian planes, you needed better instruments. The big challenge was blind flight flying when you couldn't see the ground.
Ah, navigating by instruments alone.
Exactly. So they developed radio beacon direction finding, and by the late 20s, they actually managed the first safe blind landing using instruments and, well, pretty basic radio guidance.
Wow. In the 20s, that's impressive. And the 30s built on that.
Yeah, the 1930s saw the first all-radio-controlled blind landing. Plus, the network of ground-based radio navigation just kept expanding.
And pilots started needing certification for instrument flying.
That's right, especially airline pilots. But they also hit limits with the low and medium frequencies they were using. Problems at night, in bad weather.
So they needed something better.
Precisely. That pushed research into higher frequencies, VHF, and even the very early ideas behind radar. It was all about making flight possible regardless of conditions.
Which brings us to the 1940s and World War II. Another huge catalyst, I imagine.
Absolutely. Even more urgency for reliable comms and navigation. VHF really came into its own then for both.
And landing systems.
Yep, the first instrument landing systems, ILS, started getting installed mid-decade. And the VOR network, very high-frequency, omnidirectional range that began towards the end of the 40s.
And a huge invention happened then, too, didn't it?
Critically, yes. The transistor, invented in the 40s, that completely changed the game, paving the way for modern, small, reliable, solid-state electronics. Huge shift.
So, post-war, the space age, civilian air travel explodes. What happens with avionics?
It's all about refinement and growth,
Yeah.
improving the systems they had. The 60s were key for solid-state radios, smaller, tougher, lighter gear.
And the space race influenced things, too.
Definitely. The demands of spaceflight and the Cold War pushed guidance systems and satellite navigation concepts forward. People started thinking about positioning from space.
Leading eventually to GPS. What were the big steps there in the late 20th century?
Well, the 70s and 80s were about validating the satellite nav concepts. Then came the launch of the first block-eye GPS satellites.
Was Loran still around then?
Yeah, Loran, the ground-based system, was being built out around then, too. But GPS kept developing. Block 2 satellites launched in the mid-80s, and by 94, the full 20 new satellite GPS constellation was operational. Global coverage.
And then, coming into the 2000s, air traffic was getting really busy.
So busy, the FAA basically predicted gridlock by 2022. That led directly to the next-gen program.
Next-gen. That's the big overhaul happening now, right?
Exactly. A complete modernization. It relies heavily on GPS and something called ADS-B, Automatic Dependent Surveillance Broadcast, for much more efficient air traffic management. It's a huge project scheduled to run through 2025.
It really sounds like avionics development just hasn't stopped accelerating.
That's a key point in the chapter. For decades now, avionics has advanced faster than airframes or engines. The trend is always smaller, lighter, more powerful, more reliable, using micro and even nanotech now.
Okay, let's dig into the electronics behind all this. Analog versus digital. What's the fundamental difference?
Okay, so electronics is basically about using electrical signals to represent or control things in the real world. Analog does this with continuous signals.
Like a dimmer switch for a light, or a volume knob.
Exactly like that. Or a microphone turning sound waves into a continuously varying voltage. The problem is analog signals can get easily messed up by noise or interference. Any little bit of static changes the signal. Early avionics were all analog using vacuum tubes.
Right, and digital is different how?
Digital uses discrete values. Think on or O/F, ones and zeros, usually represented by voltage being present or absent.
Like a light switch, just on or off.
Precisely. The huge advantage is that small amounts of noise don't really affect it. A 1 is still a 1 even if the voltage fluctuates a bit. It's much more robust. That's why digital dominates modern avionics. It allows for way more complexity and reliability.
You mentioned vacuum tubes for analog. Sounds old school. What did they actually do?
They were literally electron control valves, controlling the flow of electrons in a vacuum. The chapter mentions a few types. Diodes acted like one-way valves for AC current. Let it flow one way, blocking the other, turning AC into pulsating DC.
Okay.
Then triodes. They added a grid. A small voltage on the grid could control a much bigger current flow between the other parts. That's amplification.
Making signals stronger.
Yep. And tetrodes added another grid to help them work better at higher frequencies. But the key thing is, they were glass tubes, relatively big, used a lot of power, generated heat, and were sensitive to vibration. Not exactly ideal for an airplane.
No kidding. So solid-state devices came along, much better suited, you said?
Massively better. Longer life, super reliable, tough. They can handle the shaking and temperature changes. And the key ingredient is semiconductor materials.
Semiconductors. We hear that word all the time. What makes them special?
Well, they're materials that aren't great conductors like copper, but they aren't great insulators like rubber either. They're somewhere in between. It comes down to their atomic structure, specifically the electrons in the outermost shell, the valence shell. How easily those electrons can move determines conductivity.
And silicon is a key one.
The most common one, yeah. Silicon has 4 valence electrons. In a pure crystal, it shares them with its neighbors, forming strong bonds. So pure silicon is actually a pretty poor conductor, not many free electrons.
So how do you make it useful if it's a poor conductor?
That's where doping comes in.
Uh-oh.
You deliberately add tiny amounts of impurities. Adding one type of impurity creates N-type silicon, which has extra free electrons ready to move.
N for negative extra electrons. Got it.
Right, and adding a different impurity creates P-type silicon, which has holes, places where an electron should be. These holes can act like positive charges moving.
P for positive holes. Okay.
And the real magic happens when you join N-type and P-type material together. That creates a PN junction.
Which is the basis for a diode.
Exactly. At that junction, you get a depletion area, sort of an electrical barrier. If you apply voltage the right way forward, bias, negative to N, positive to P, electrons and holes are pushed towards the junction, the barrier shrinks, and current flows.
And if you apply voltage the wrong way, reverse bias.
The barrier gets wider, and it blocks the current. So it's that one-way street action again, perfect for rectifying AC to DC.
The chapter mentions Zener diodes, too. Different how?
Zener diodes are special. They're designed to actually conduct current in reverse without being damaged once a specific voltage, the Zener voltage, is reached. They're used a lot for voltage regulation, keeping voltage steady.
Okay. Now, transistors. The real workhorses, you said. Switches and amplifiers. How are they built?
Right. A standard transistor, a BJT, is like a sandwich NPN or PNP layers. You have 3 connections.
Yeah.
Emitter, collector, and the base in the middle.
And the base is the control.
Exactly. A tiny current or voltage applied to the base controls a much, much larger current flowing between the emitter and collector.
So you can use that small base signal to turn the large current fully on or OFF, like a switch.
Yep. Or you can vary the base signal and make the large current vary proportionally, which is amplification.
Got it. The chapter listed a few other solid-state devices too, SCRs, triacs.
Yeah, just quickly. SCRs, silicon-controlled rectifiers, are like diodes with a gate terminal. A quick pulse on the gate turns them on in, and they stay on until the main current drops. Good for power control.
Okay.
Triacs are similar, but work with AC, controlling current in both directions. UJTs, unijunction transistors, are simply used in some timing circuits, though less common now.
And FETs, field effect transistors.
FETs are a bit different. They use an electric field created by voltage on a gate to control current flow through a channel. They're voltage controlled, unlike BJTs, which are current controlled.
Two types mentioned, JFs and MOSFETs.
Right, junction FETs and metal oxide semiconductor FETs. MOSFETs are everywhere in digital circuits today. They're very efficient.
Amazing how many different functions you can get just by layering these N and P materials differently. What about light? How do semiconductors interact with light? Photodiodes, LEDs.
Yeah, light is just energy, photons. When photons hit a semiconductor, they can knock electrons loose, creating current. That's a photodiode current proportional to light intensity.
Used for light sensors, maybe?
Exactly. Phototransistors take that effect and amplify it using a transistor structure. And LEDs, light-emitting diodes, work the other way around.
They make light instead of detecting it.
Right. When you force electrons and holes to recombine in certain semiconductor materials, like gallium arsenide, they release energy as photons visible light. Different materials give different colors. That's why LEDs are so common in cockpit displays now: efficient, long-lasting, small.
Okay, let's shift to basic analog circuits. Digital might rule now, but analog's still around. Rectifiers we covered turning AC to DC. What about amplifiers?
Amplifiers boost signal strength. Transistors are key here. A common emitter amplifier gives good current gain but flips the signal phase 180 degrees. Good for weak signals like microphones.
Needs careful setup, though. Biasing.
Yes, you need to apply DC voltages biasing to keep the transistor in its active amplifying region for the AC signal. Gain is measured by beta.
And common collector amplifiers.
They have different characteristics. Output follows the input current, no phase shift. Good for matching impedances between circuits. Also needs biasing.
Okay, and oscillator circuits.
Yeah.
Making AC from DC.
Right. A basic concept is the tank circuit, just a capacitor and an inductor. Energy sloshes back and forth between them, creating an oscillation.
But it fades out, right? Due to resistance.
It does, it's damped. So transistor oscillators like the Hartley use a transistor to actively feed energy back into the tank circuit, keeping the oscillation going.
And the frequency depends on the capacitor and inductor values.
Primarily, yes. For really precise frequencies, you use crystal oscillators. They rely on the piezoelectric effect in quartz crystals. They vibrate at a very stable frequency when voltage is applied.
And multivibrators.
They use two transistors switching each other on and off alternately, good for generating square waves or other non-sinusoidal shapes.
That covers the analog building blocks well.
Yep.
So moving to digital electronics, how do transistors become logic gates?
In digital, transistors act as simple switches fully on, representing logic 1, or fully ORFF, logic 0. Logic gates combine these switches to perform logical operations based on their inputs.
Can you run through the basic gates, not AND-OR?
Sure. Not as simple. One input, output is the opposite. Input 1, output 0, output 1. It inverts.
Okay.
A buffer just passes the input to the output, maybe strengthens the signal or isolates circuits. And D-gate output is 1 only if all inputs are 1.
Got it. All or nothing.
Output is 1 if any input is 1.
At least one. Makes sense.
NAND is not ND. Output is 0 only if all inputs are 1. ANOR is not OR. Output is 1 only if all inputs are 0.
Okay, the inverted versions.
An exclusive OR, XOR output is 1 only if the inputs are different. One is 1, the other is 0.
Right. These gates have standard symbols and truth tables, to abstract away the electronics.
Exactly. Designers work with the logic symbols and tables. These simple gates are the building blocks for everything: digital microprocessors, memory, everything.
And in the cockpit, this leads to digital displays and controls.
Absolutely. Digital data displays are everywhere now, showing flight info clearly. And digital tuners and audio panels combine controls for many radios into one interface. Much cleaner, more capable.
Let's talk radio communication then. How planes actually talk wirelessly. It all starts with radio waves, right?
Right. Electromagnetic waves, part of the spectrum. Key properties are frequency, cycles per second, hertz, and wavelength, distance between peaks. They're inversely related. Higher frequency means shorter wavelength.
And aviation uses a whole range of frequencies.
It does, from LF, low frequency, way up to SHF, super high frequency. The FCC controls who uses what. Generating them is basically applying AC to an antenna.
An antenna of the right size.
Yeah, often related to the wavelength, like half a wavelength long. The oscillating current creates electric and magnetic fields that radiate out at the speed of light, about 186,000 miles per second.
And different frequencies behave differently in the atmosphere? VLF, LF, MF?
Totally. Those lower frequencies, VLF, LF, MF, have long wavelengths. They tend to follow the Earth's curve as ground waves. Good for long distance, used in systems like ADF.
About HF, high frequency.
HF waves travel in straight lines but can bounce off the ionosphere, the charged layer high up. Sky waves allows for very long-range communication over mountains and stuff.
And VHF and UHF.
Yeah.
Very high and ultra high frequency.
Those are mostly line of sight. Transmitter and receiver need to see each other, more or less. VHF is crucial. It's the main band for air traffic control, voice comms, plane-to-plane chat. That's 118 to about 137 megahertz. UHF is used for things like ILS glide slope, DME, radar, satellite links.
So how do you put information voice data onto these waves? Modulation.
Exactly. Modulation is changing the carrier wave somehow to encode the info. AM, amplitude modulation, varies the strength or amplitude of the wave.
Like making the wave taller or shorter.
Yeah, in sync with the voice signal, for example. FM, frequency modulation, varies the frequency slightly, keeping the amplitude constant. FM tends to be less prone to noise.
And SSB, single sideband.
SSB is a more efficient type of AM, mainly for lower frequencies like HF. It suppresses the main carrier wave and one of the two sidebands created during modulation. Saves power and bandwidth.
Okay, so you need transmitters and receivers. What do they do?
Transmitter generates the precise carrier frequency, amplifies it, modulates it with the information, and sends it to the antenna. Often uses frequency multipliers to get stable, high frequencies.
And the receiver?
Receiver grabs the weak signal from its antenna, amplifies it, filters out unwanted frequencies, separates the carrier from the info, demodulation, and amplifies the info for output, speaker, display, whatever.
Many receivers use that super heterodyne thing.
Yeah, it's a clever trick. Mixes the incoming radio frequency with a locally generated frequency to create a fixed intermediate frequency, or IF. It's easier to amplify and filter that fixed IF really well, improves sensitivity and selectivity.
And the antenna is key at both ends. What matters for antennas on planes?
Size is critical, related to wavelength. VHF half-wave might be a few feet long. Quarter-wave Marconi antennas use the aircraft skin as a ground plane.
Polarization. Horizontal or vertical?
Right, orientation of the electric field. Transmitter and receiver antennas need to match for best signal. Directivity matters too. Some are omnidirectional, sending receiving all around. Others are directional focused.
What types are common?
Dipoles, often V-shaped for VOR. Marconi vertical whips for VHF comms. Loop antennas, which are direction sensitive, used in ADF systems.
And they're connected by special cables.
Coaxial cable, COAX. Designed to carry the signal efficiently with minimal loss. Matching the impedance, usually 50 ohms, between the radio, cable, and antenna is vital for good performance.
Okay, that covers comms. Let's switch to radio navigation. Big step up from map and compass.
Huge step. Especially for flying in clouds or bad weather. Early systems were pretty basic, Morse code ranges and such. Modern stuff is much more precise.
Let's start with VOR. Still a workhorse system. How does it work?
VOR stations on the ground transmit VHF signals. The aircraft receiver uses these signals to figure out its bearing, or radial, from the station. Think of 360 spokes radiating out from the VOR, numbered by magnetic degrees.
How does it know which radial it's on?
It compares the phase difference between two signals the VOR sends out, a reference signal and a variable signal. The phase difference corresponds directly to the radial.
And the pilot sees this on?
A course deviation indicator, CDI, shows if you're left or right of the selected radial. Has a tow from flag too, tells you if that radial leads towards or away from the station.
Often integrated into fancier displays too, HSI, EF.
Oh yeah, RMI, HSI, glass cockpit displays, they all show VOR info. VORs are often paired with a DME or ILS components.
Okay, ADF next, automatic direction finder. Uses NDBs.
Right. NDBs, non-directional beacons, are ground stations transmitting on lower frequencies, LFMF. The ADF receiver in the plane has a loop antenna that can sense the direction the signal's coming from.
How does it point?
Older ones physically rotated the loop to find the null or weakest signal. Modern ones use fixed loops and electronics, a goniometer, to figure out the bearing. The ADF needle in the cockpit points right at the NDB.
And RMIs combine ADF and VOR.
And compass heading, yeah, very useful. NDBs identify themselves with Morse code. You can even tune in AM radio stations sometimes for rough bearing, though that's not for primary navigation.
ILS instrument landing system. Vital for low visibility landings. What are the pieces?
Key parts are Localizer for horizontal guidance, runway centerline, VHF. Glide slope for vertical guidance, descent angle, UHF. Marker beacons for distance checks along the approach, 75 megahertz, and sometimes compass locators, low power NDBs at the markers.
How do the localizer and glide slope provide guidance?
They both transmit two overlapping beams, modulated at 90 Hz and 150 Hz. The receiver measures the difference in strength between the 90 and 150 Hz tones. If they're equal strength, you're right on course, localizer, or on the glide path, glide slope. If one is stronger, the CDI needle deflects, showing you which way to correct.
Where are the antennas for those?
Localizer is usually at the far end of the runway. Glide slope antenna is typically off to the side near the touchdown zone. Marker beacons give audio tones and lights in the cockpit as you fly over them. Outer, middle, sometimes inner marker.
DME distance measuring equipment tells you how far away you are.
Exactly. Slant range distance to a ground DME unit, often co-located with a VOR or ILS. The aircraft sends out pulses, interrogates, the ground station replies after a tiny delay. The airborne unit times the round trip, does the math, and displays distance in nautical miles.
Can it do speed and time, too?
Yeah, by seeing how fast the distance is changing, it can calculate ground speed relative to the station and time to reach it. Uses UHF frequencies.
RNAV area navigation. Sounds more flexible, flying direct routes.
That's the idea. Instead of just flying VOR to VOR, RNAV lets you define waypoints anywhere and fly direct routes between them. The onboard computer uses VOR DME signals, or GPS now usually, to calculate position and provide guidance along the programmed route. Much more efficient.
Okay, switching gears slightly. ATC radar, how controllers track planes, primary versus secondary.
Primary radar is the basic skin paint radar, sends out a pulse, waits for a reflection off the aircraft, gives range and direction, but not identity or altitude.
Just a blip on the screen.
Pretty much. Secondary surveillance radar, SSR, is cooperative. The ground station sends an interrogation signal, 1037 MHz, and the aircraft's transponder replies, 1090 MHz, with a code.
That code gives identity.
Mode 3A gives the assigned ID code. Mode C adds altitude information. Mode S is even more advanced, allowing for more data exchange. SSR is how ATC knows who is who and how high they are.
TCS traffic collision avoidance system. That's plane to plane.
Yes, an airborne system. It interrogates transponders on nearby aircraft. If it detects a potential collision risk based on proximity and closure rate, it issues alerts.
What kind of alerts?
First, a traffic advisory. TA, hey, look out, traffic there. If it gets critical, a resolution advisory, RA, climb, or descend. Specific instructions to avoid collision. It's an independent safety net.
ADS-B, the next-gen cornerstone. How's it different from radar?
It's fundamentally different. With ADS-B out, the aircraft broadcasts its own position, altitude, speed, etc., derived from its GPS. It's automatic and dependent on the aircraft's own systems, hence the name.
So it's not waiting to be interrogated?
Nope. It just broadcasts periodically on either 1090 MHz, like Mode S, or 978 MHz, UAT. Other aircraft with ADS-B in and ground stations receive this data.
Advantages.
More accurate position than radar, especially in remote areas. Provides traffic info directly to pilots with ADS-B and better situational awareness. Lower infrastructure costs than radar. It's a big shift.
What about radars on the plane? Radial altimeter, weather radar.
Radial altimeter looks straight down. Measures height above ground level, AGL, using radar pulses. SHF band around 4.3 gigahertz. Crucial for low approaches, gives exact height over terrain right below.
And weather radar.
Looks ahead. Transmits microwave pulses, SHF, 510 gigahertz range, and detects reflections from precipitation, rain, hail, snow. Shows intensity and location, helps pilots avoid the worst weather. Lightning detection is also available. Plus, increasingly, satellite weather data is uplinked to the cockpit.
ELT, emergency locator transmitter. Safety beacon for crashes.
Exactly. Designed to activate automatically in a crash and transmit a distress signal. Older ones use 121.5 and 243.0 megahertz analog signals being phased out.
Why phase out?
Lots of false alarms, less precise location. Modern ELTs use 406 megahertz digital signal, monitored by the Cospa-Sarsat satellites. Much better.
Digital signal carries more info.
Yes, unique aircraft ID and often GPS coordinates. Leads to much faster, more accurate rescues. Testing them properly is critical to avoid false alarms.
Chapter mentioned Loran briefly. Mostly gone now.
Yeah, Loran was a ground-based long-range system using low frequencies. Timed pulses from multiple towers gave position, but GPS accuracy and coverage basically made it obsolete in the U.S.
And GPS itself, global positioning system, satellite-based. How does it pinpoint location?
It uses signals from a constellation of 24-plus satellites orbiting Earth. Each satellite broadcasts its position and a very precise time signal. Your GPS receiver listens to at least 4 satellites. By measuring the tiny differences in signal arrival times, it calculates its distance from each satellite.
And figures out its position from those distances.
Right, through trilateration. Gives latitude, longitude, and altitude. Amazing accuracy.
FAA improves GPS accuracy even more. Wide area augmentation system.
It does, specifically for aviation. Ground stations monitor GPS signals, figure out any errors, and generate correction messages. These corrections are sent up to geostationary satellites, which broadcast them down to WAAS-enabled GPS receivers in aircraft.
So corrects the GPS signal in real time.
Essentially, yes. Provides the accuracy needed for precision approaches, similar to ILS, but using GPS. Huge benefit, especially at smaller airports without full ILS.
Then there's INSRRs, inertial navigation reference systems. Totally self-contained. No radio signals needed.
Correct. They use internal sensors accelerometers to measure linear motion and gyroscopes to measure rotation. Starting from a known position, the system constantly calculates velocity, attitude, and change in position by integrating these measurements over time.
Sounds complex. Early ones use mechanical gyros.
Yes. Modern IRS use ring laser gyros or fiber optic gyros. Much more reliable, solid state. They're incredibly accurate short-term, but tiny errors can build up over long flights.
So they're often paired with GPS.
Very common. GPS provides periodic position updates to correct any drift in the IRS. The combination is extremely robust and accurate.
Last system mentioned. ACARS, Aircraft Communication Addressing and Reporting System. That's more data link.
Exactly. It's a digital data link, mostly VHF, between the aircraft and the airline's ground operations. Sends automated reports, engine data, fuel status, position reports. Receives messages too, weather updates, flight plan changes, gate info. Improves efficiency.
Wow, it's a huge range of systems. Okay, the chapter also covers installation and maintenance. What are the key things technicians need to know?
It's highly regulated work. Most complex repairs need certified repair stations. A&P techs handle removal installation, inspections, basic troubleshooting, but always following the manuals, aircraft manual, equipment manual.
New installations need approvals, PSOs, FAA forms.
Definitely. Equipment usually needs to be TSO, Technical Standard Order approved. Major alterations require specific FAA paperwork, like a Form 337 or maybe an STC, supplemental type certificate. Airworthiness is paramount.
What about practical considerations for installation?
Space is always tight on planes. Weight and balance are critical. Power consumption needs to be accounted for, and you need to be able to get to it later for maintenance.
Mounting, wiring.
Secure mounting, proper racks. Careful wire routing, avoid high heat, flammable fluids. Ensure proper cooling airflow. Vibration isolation is key too, using shock mounts and making sure they're properly bonded for electrical grounding.
Bonding. To reduce radio interference.
Yes, bonding connects all the metal parts together electrically, prevents static buildup, provides a good ground path. Shielding wires also helps. And those static dischargers you see on wingtips, they bleed off static charge into the air. All crucial for clean radio performance.
Antenna installation sounds critical too.
Absolutely. Mechanically secure, of course. Electrically matched to the system. Located correctly for good signal coverage, avoiding blockage. Correct polarization. Installers use specific templates and procedures.
And the coax cables connecting them.
Right type, right length. Connectors install perfectly. Securely routed, respecting bend radius limits to avoid kinking or damaging the cable. Maintenance involves checking all these things: connections, wiring, bonding, shock mounts, and always operational checks after any work. ELTs have specific inspection schedules too.
Okay, well, the learner, we have covered a lot of ground here diving into avionics. What's the big takeaway, would you say?
I think the main thing is just how complex and vital this field is. Avionics is constantly evolving, absolutely essential for safe, efficient flight today. It spans this huge range from basic analog ideas to incredibly sophisticated digital and satellite systems.
It really is a remarkable journey, isn't it? From just getting voice comms working to navigating globally with pinpoint accuracy. Easy to forget things like Morse code navigation or how much wartime pushed the technology. We really hope this deep dive gave you, the learner, a useful shortcut to understanding the whole fascinating area.
And looking forward, it makes you think, doesn't it? With avionics advancing so fast, especially with autonomous flight becoming more real, What are the next big challenges, maybe even ethical questions, for communication and navigation in the future?
That is definitely something to ponder. We hope this has sparked your interest and given you a good grounding. If you have more questions or want us to dive deeper into specific systems next time, let us know.
Yeah, absolutely.
Until then, keep exploring.